This video is about the heating curve of water. So what happens is that when you heat up ice all the way to gas, so you literally start off with a cup of ice on the hot plate and you heat it up all the way until it starts to boil and so forth, you get this graph, and it looks very similar to this one. So what you have to be able to do with this graph is, one, you have to tell me what all these little lines mean and what they stand for, and then two, you have to be able to tell me some math. Okay, so what does all this mean? If you started off at a very cold temperature, because on our on our y-axis is temperature, on our x-axis is heat added. So over time, you are adding heat. It's on the stove. Okay, and as you can tell, as you add heat, which you should know, your temperature goes up. Sometimes there's some points where the temperature does not rise, and we're going to talk about that in just a second. So when you start off, the temperature is extremely low because you have a solid. Okay, so on this first line here, what's happening is you have a solid that the temperature is increasing. Now, over time, what will happen to that ice? It will go from a solid to a liquid. Now, that is not this part right here. It's not a full liquid there. We're going to talk about what that line is in just a second. Here, between C and D, is where you have a complete liquid. Then, over time, it'll start to boil, and eventually all of it will turn into a gas. Okay? So you have all three phases are shown in this. Now, how do they get there? Because you don't go straight from a solid to a liquid without any in-between time. You have to have a point where you still have some solid and then you have some liquid. This is called your melting and freezing point. So this line here, as you go this way, means you are melting. The substance is melting. As you go this way, if you were to go back and you take heat away, that means it is freezing. Okay, so what these flat lines mean, these plateaus as I like to say, is your phase changes. So the flat lines are your phase changes. Now, what happens as you go from a liquid to a gas? If you go this way, it's vaporization. This way, condensation. Okay, so it all depends on whether you're gaining or losing heat. Now, another thing that you need to make sure that you know is that these lines are flat for a reason. Because during a phase change, temperature remains constant. Now, what does that mean? That means as the actual phase is happening, the temperature does not increase. As much as you may think it does, you would think maybe that this line should just be straight on up, no plateaus or anything like that. But that's wrong. All the energy is going towards actually melting the substance, that the temperature does not change. Okay, so you need to make sure that you know this right here. During the phase change, temperature remains constant. It remains the same. Now, there's one other piece that this tells you, and that is on this line here, if you were to go over, the temperature that's actually on this axis here is going to be your melting and freezing point. Okay, so the temperature that's here on this axis is going to be your melting and freezing point. And if you go over here, this point is going to be your boiling point. Okay, so if you're given a graph like this, you should be able to tell me what the melting, freezing, and boiling points are of the substances. Okay, now you have to be able to analyze the graph, and that's the information that you need. Now comes the math. Okay, because there's a certain amount of energy to change the temperatures, and we've talked about that one with the specific heat, Q equals mCp delta T. But there's also a certain amount of energy required to melt, vaporize, condense, and so forth. And that's called this. The heat of vaporization is the energy required to boil, and I would probably highlight that word. Heat of vaporization is the energy required to boil 1 gram of a substance at its boiling point. So you get this equation. Q equals mHV. So Q, again, is heat, M is mass, and now we have this HV thing. Now, HV is a constant, and for water, which is the only one that you're going to have to really deal with, it's given to you on the reference table. So on the reference table, it tells you right here, as you can see, HV of water is going to be 2,260 joules per gram. This value is always given to you. So literally in a problem, you're either given the heat or you're given the mass, and you solve for the other one. It should be extremely easy. Now, use this equation when talking about boiling. This one is when you're going to talk about melting. So this Q equals MHF looks very similar, so you have to know the difference between HV and HF and when to use them. HF is dealing with melting. So again, it's given to you. You don't have to memorize it. HF, based on the reference table, is 334 joules per gram. So you just plug it in and go. Okay? So, how do you know when to use what? So here we go. You have another graph. On this graph, this is sort of like the mole roadmap and things like that. If you do what I tell you right now and you use it for the problems that we're about to do, it should be easy. Should be. What you have to know is that when you're on these lines here, you're always going to use Q equals M Cp delta T. So anytime you're just changing the temperature, you're going to use that equation. Q equals M Cp delta T. And here, Q equals M Cp delta T. There's one small catch. That, yes, you're going to use this equation, but again, looking at our lovely reference table, here, you should see it says specific heat of water. And there's 3 different values, depending on the phase that it's in. So if you're dealing with ice, you're going to use 2.05. If you're dealing with steam, you're going to do 2.02, and liquid, 4.18. So what needs to happen is anytime you're at this level on your graph, you're going to use Cp equals, it's ice at that point, so you're going to use 2.05. Here, remember it's a liquid, so Cp is going to be 4.18. Here, we are at our gases, so we're going to do Cp equals 2.02. Okay, now, our plateaus. What's happening here? We're melting, right? So that means we're going to use Q equals MHF. Okay, so MHF. Remember HF equals 334. Here, we are vaporizing. It's going through vaporization, so you're going to use HV. So Q equals MHV, and HV will always equal 2,260. So this is what you have to do. I'm going to give you 2 points on this graph, and you have to be able to calculate the Q. Now it's simple if both the points are in one line, you plug it in and solve. The problem comes in is what if my point is here, and then my second point is all the way up there. However many parts of the line, parts of the graph you go through is how many equations you have to do. Okay, so let's show you what I'm talking about. And I'm going to refer back to this graph over and over again. Okay, so the question is how many joules are absorbed by a cup of ice with a mass of 450 grams in order to raise the temperature from negative 20 degrees to negative 10. So how many joules means we're solving for Q of 450 grams, which is our mass, change in temperature. We have our T1 and our T2. Now this is what I want you to do. I want you to graph it. I want you to every single time draw this. Every single time. Okay? So this means you're going to draw this little staircase, which is this. It's the same thing. This is like the main thing it's looking at. So you're going to just do a quick thing just like it. So, and remember that here for water is 0, here is 100. So my question is where does our points fall? Where's our starting point and our ending point? And for this one, our starting point is negative 20 degrees Celsius. So on our lovely graph here, Negative 20 is going to be down here somewhere. So we're just going to put negative 20. We're going to plot the point, put negative 20. Our second point is negative 10. So that means we're there. So what does this mean? If you look back at our graph here, you can see that we're dealing on just with one line here. We're dealing with down here. So it's a change in temperature. So out of all of our different equations that we can use, we're going to use Q equals MCP delta T. So we're going to use Q equals MCP delta T. Now, the most common mistake to do is to use the wrong CP. So this is why it's important to know, okay, down here we're dealing with ice, and it also tells you you're dealing with ice. So our CP in this case is going to be 2.05, right? Because remember, looking back at this, when you're dealing with ice, it's 2.05. So then you just plug it in. So Q equals M, which is 450, CP, which we've established is 2.05 because it's ice. Change in temperature is going to be negative 10 minus negative 20, which is 10, and then you solve. So 450 plus 2.05 plus 10. Based on sig figs, you get 2 sig figs, so 460 joules. Okay, now the most common thing for students to get wrong is to use that wrong CP. So this is why it's important. Next example. How many joules of heat are necessary to completely melt 525 grams of ice at its freezing point? Now this is what students do. They read this, they see one number, and then they leave it blank because they have no idea what to do with just one number. Okay, it's not that hard. You just have to listen to my steps here. So again, draw a little lovely staircase thing and figure out where you're starting and where you're ending. So it says how many joules, so we're trying to find Q, are necessary to completely melt 525 grams, so that's our mass, of ice at its freezing point. So the question is, which one of these lines deals with melting? Right here. So looking back at our lovely graph, which equation are we going to use? What does this represent on here? Okay, so we're going to use Q equals MHF, because remember HF is dealing with the melting. That's why we highlighted that words in our notes. So you're using Q equals MHF. You're solving for Q. M is 525, and then HF, remember, is on the reference table, is 334. So you just have to take those numbers, 525 times 334. And you get an extremely big number, but you're only allowed 3 sig figs, so 175,000 joules. Okay? Again, the only reason students miss this is because they have just one number there and they have no idea what to do with it. So let's try one more. And this is the hardest one. This is where I'm talking about doing that graph, and doing this is going to help you. Now you might need a little bit more space than what's provided on the paper for you, so you may want to get out a piece of notebook paper or something. So we need to figure out our starting and ending point. So it says how many joules of heat are necessary to increase the temperature of 25 grams. So this is our mass of water at 78 degrees Celsius. So that's our T1, of 120 degrees Celsius. So that's our T2. Now, looking at the graph, you have to figure out where those two temperatures are. So you also have to remember that this one for water is 0, and this is 100 for water. It boils at 100 degrees Celsius. So 78, does it fall below 0, between 0 and 100, or above 120? So for this, it's somewhere between 100 and 0. So it's going to go there. Our second point is 120, which obviously falls above 120. So here's what happens. There's not a straight line between 78 and 120. There are actually 1, 2, 3. There are 3 lines between those 2 points. So guess what? You have to do 3 equations and then add them up for your answer. This is why this can get a little bit tricky. Okay, the most common mistake is to plug in Q equals MCP delta T and plug in and go. You cannot do that. Okay, they're on different lines of the graph, so you have to break it down. So this means what we're going to do is this red section, we're going to call that Q1. So we're going to solve for Q1 first. So we're on a slant. So anytime you're on a slant, you're going to use MCP delta T. Slant means the temperature's changing, so that's the equation we're going to use. So we're just going to plug in. M is 25 throughout the entire thing. CP, we're in the middle section of the graph, which means we're going to use 4.18, okay, because it's a liquid. Now, change in temperature is where it gets hard. Change in temperature for this one. What is happening in this red segment? Where is it starting and where is it ending? It's starting at 78, but it's stopping at 100. So your change in temperature is going to be 100 minus 78. And you have to plug it in and solve. Okay? So you see that that red mark stops at the 100, not all the way up to 120. So we solve. So 25 times 4.18 times 100 minus 78. And do not round anything until the very end, so 299 joules. That's the first segment. The second segment, which we're going to call Q2, is a plateau, is a flat line. So the question is it MHV or MHF? Well, it's on the 100, so that means it's boiling, which means we're going to use MHV. So we just plug in M 25. How do we know HV? Is because it's on the reference table and it tells you 2,260. And you solve. Okay? So that tells us how much heat's required for that part. And then last, this piece here, 120. It's going from 100 to 120. So this is our Q3. We're on a slanted line again, which means we're going to use MCP delta T. M 25. CP is not 4.18 this time. This is why we can't just cram it all together. This time we're dealing with our gases. So if you refer back to this lovely thing again, for our gases, the CP is always going to be 2.02 times the change in T. And this is where students get lost again. The change in temperature is always the T2 minus the T1. So for this green section, it's going to be 120 minus 100. Because again, you're starting at the 100 mark for the green piece and going up. So now we just solve. So 25 plus 2.02, not plus, sorry, 25 times 2.02 times 120 minus 100 gives you that. Now, final answer. What do? This gives us part of the graph. This gives us another part and another part. So to get the full amount of energy, we need to add them up. So to get our final answer, you're going to do Q1 plus Q2 plus Q3. So Q equals 2,299 plus 565,000 plus, or sorry, 56,500 plus 1,010. Solve that, and that's your answer. So 2,299 plus 56,500 plus 1,010. Sig figs, you're only allowed 2 sig figs, which is, this one's a little bit tricky. So in your calculator, this is what you get. So to get just 2 sig figs, you actually have to do this. 6.0 times 10 to the 4th joules. And that's it.